Okay, so here we are going to find a to the power of 7 for this matrix A. We could, of course, just multiply this thing out, a times a bunch of times, but that probably will actually be more work than the diagonalization process, assuming diagonalization works. So yeah, we're going to go ahead and try that. So as always, the first thing we need to do is get our eigenvalues. And so I'm going to do lambda I minus A is going to be lambda minus 2, -3, -1, 0, lambda minus 1 and -2, and 0, -3, and lambda minus 2. And so our determinant is going to be lambda minus 2. I'm just going to use that first column because of all the zeros, times lambda minus 1, -2, -3, and lambda minus 2. So I'm going to get lambda minus 2 times lambda squared minus 3 lambda. That'll be plus 2 minus 6, so minus 4. And so it looks like we get lambda minus 2, lambda minus 4, and lambda plus 1. And so from there, we are going to get all of our eigenvectors. So we have 2, 4, and -1. So at lambda 1 equals 2, I'll get my 2i minus a is 0, -3, and -1, 0, 1, and -2, and 0, -3, and 0. So if we ignore the leftmost column, it's just sort of two entry things. And I can see that I'm not going to be able to like wipe out any whole rows really like immediately. Like none of they're not all multiples of each other. So like I know this is a pivot, for example, and no matter what reduction I do, I'm going to get a second pivot in that third column. So the only free one that I've got is the first one. And so this is going to just give me, I guess I'll say x equals t. And from these two equations that are resulting over here, the three equations, we should have that y and z are both 0 if we were to find that null space. So here we will have our vector, and I'll just set t to be 1, and I'll get this one. And then I'm going to need to get my lambda 2 equals 4. So 4i minus a. And this one's going to look a little different. So I'll get 2, -3, and -1, 0, 3, and -2, and 0, -3, and 2. So here I can see the second and third rows will just sort of cancel one from the other. And that does leave us with 2 pivots, and this is going to be free. So just because of the numbers that are there, I'm going to let that be 3t. So I'm going to let z be 3t. And then if I work my way back, this is going to give me y is 2t. And then just working back again, what I get is that 2x minus 6t minus 3t is 0. So it looks like my number's not the best here. So what I'm getting is x is 9 over 2t. So I'm just going to use 2t for this to get a nice vector. That way it's going to cancel out the denominator up here. Make sure you see that's a 9. And so I'll end up with a 9, 4, and 6 for this one. And then my last one, I have enough space here, hopefully. Lambda 3 is -1, So negative I minus A is going to be -3, -3, and -1. 0, -2, and -2. And 0, -3, and -3. And again, finding the null space of this. The third row is just 1.5 times a second, so I can use it to get rid of that. And again, just kind of want to be cautious here. Just going to choose a t for this. I'm going to let z be t. This tells me that y is -t, and then this gives me -3x plus 3t minus t is 0. So x is 2, I think -2t over 3. No, that's positive 2t over 3. Okay, I'm erasing everything but the thing I wanted there. And so I'm just going to choose a t to make some nice integers. I'll just choose t equals 3 for this. And that's going to give me my vector. So x3 is going to be, plugging that in. So 2, -3, and 3. Okay, so next what we have to do is actually now compute. And that is going to be a little bit of work, so I need to get some space for myself here. Let's make this a bit smaller. And so we're going to use the formulas that we've got. So a to the 7 is going to be equal to basically p d to the 7 p to the -1 for d equals p to the -1 a p. And we do construct that p using the eigenvectors. So I'm going to construct the p as the first eigenvector 1, 0, 0, the second eigenvector 9, 4, 6, and the third eigenvector 2, -3, and 3. And using whatever method you want for inverse, I'm just going to throw that in front of you and hope that you know how to get it. So I have 1, it's kind of ugly, -1/2 and -7 over 6, 0, 1/10, and 1/10, and 0, -1/5, and 2/15. So yes, it's a little bit ugly. Throw it into a Symbolab or any sort of online calculator, but you can get that. And then with that arrangement, D is going to follow the same arrangement for corresponding eigenvalues. So 1, 0, 0 came from 2, 9, 4, 6 came from 4, and the 2, -3, and 3 came from -1. So that's going to be my D. And so, yeah, I just have to throw this into the formula now. This does mean that d to the 7 is going to be 128, 0, 0. This is a 5-digit number, but it's a number, 16, 3, 5, 4, and 0. And then -1 to the 7 is -1. And so a to the 7 is going to be p times d to the 7. So this matrix here. And then p to the -1, so that's that ugly inverse. And it's just going to be matrix multiplication from now, so we do have to put the 3 together, but it's not so messy, and we reduce the whole thing. And we're going to end up with 128, 14,682, 14,596, 0, 6,553, 6,554, 0, 9881, and 9830. If you did make any kind of mistake in this in any of the computations, what's likely to end up happening for you is that some of these fractions are going to be off somewhere, and then your final answer here is going to end up with some kind of fractions in it, most likely. And that shouldn't really make any sense because A was an integer matrix, and if I keep multiplying and adding integers together, I still have integers. So you should be able to sort of check some work here. If you end up with fractions, that's not going to likely be the right answer. So if you're stuck on a test and doing something, that's maybe a way that you can kind of figure out you need to go back and fix something.